Welcome back, students. In the previous videos, we were talking about the Lcr circuit and also the phasor diagram. Today, we are going to start a new topic, which is resonance. Resonance in electrical circuits. Well, we have come across resonance in the 11th standard when we studied the lesson on oscillations. But we were studying about mechanical resonance. So what is resonance? Well, you have a system that oscillates with a natural frequency. Let's say I take a pendulum. So this is a pendulum. This has a natural frequency, and it, like if I allow it to oscillate, then it will have a time period of oscillation. And that is given by this expression, right? So the time period of oscillation is given by 2 pi square root of L divided by G. So the time period depends only on the length of the pendulum. So if I calculate the length from this point to the center of mass, then that would be the length of this pendulum. If I know that value, and if I substitute that in this equation, and I know anyway the value of G, so then I can get the period of oscillation for this pendulum. Okay. So this period or this frequency is called as a natural frequency of this pendulum. So this is a natural frequency. It depends only on the length, nothing else. I can have this body, or I can have a stone, or I can even have a pen like this, and if so long as the length remains the same, then the period of oscillation will be the same for all these different pendulums. So and the frequency of this pendulum is called as the natural frequency of the pendulum. So it has this natural frequency, it is oscillating now. And I am going to drive this pendulum with an external energy source. In this case, it's me. I am the external energy source for this pendulum. And you see, if the external energy source is also having the same frequency as a natural frequency, then I get the maximum amplitude of this oscillation. You see, I had to wait for it to come back. So it takes so much time to start from here and then come back, and my hand also hits it with that frequency. When it comes here, it hits. When it comes here, it hits. So the time period between one hit and the next is the same as the frequency of as the time period of this pendulum. So if the external frequency is the same as the natural frequency of the system, then I get the maximum amplitude. So this is the resonance condition. Okay, so now you have resonance actually. What you're seeing is resonance. Instead, like if I did something else, if I keep doing, like if I keep changing the frequency, then you see you don't have the same amplitude now. Okay. But if I allow it to come back, and then if I match this, you see, if the frequency of the external energy source, that's me, is the same as the natural frequency of this pendulum, then it has the maximum amplitude. So this happens in the case of a mechanical system. So if a system oscillates, then it can have resonance. And let's talk about the electrical system now. AC is actually oscillations. So when you supply a voltage, it starts from 0, it goes to a peak, and then it goes to a minimum, comes back to 0, and keeps doing it all the time. So that is AC. So there is oscillations. So if there is oscillations, then you can expect resonance. In the resonant condition, the amplitude of the oscillations must be maximum, as we just saw. For a particular amount of energy you provide, you will have the maximum oscillation there. If you provide more energy, then the amplitude will be more, but for a certain amount of energy, then if you have the frequency matching with the natural frequency, then you will have the maximum oscillations, the maximum amplitude for the oscillations. Okay. So what would be the equivalent here? What is the system here, first of all? Here, in the case of the pendulum is a system, the mechanical system, and then my hand was external driving source. Okay, so what is a system in the case of an electrical circuit? In the case of an electrical circuit, I don't need this anymore. So okay, I don't need this anymore. This is a mechanical system. In the case of an electrical circuit, the circuit without the power source is the system. Okay. You see, this is a system. Suppose I have a resistor circuit. This is a system. Or if I have a capacitor, that's the system. And if I have an inductor, that's the system. So the battery I connect, so the battery or a source, the power source I connect, that's the external source that drives this circuit. Okay? So the system can be either this, or this, or this, or it can be something like this too. Okay, it can be something like this too. Or it can be something like this too. Or it can be something like this too. So these are the systems. These are the electrical systems. Okay, and then when I connect a voltage source across this, then that is what is driving this. So when I say this is a system, would it have a natural frequency? Well, this will not have a natural frequency. This will have a natural frequency, and this also will have a natural frequency of oscillations. We'll get to that a little later. Okay? So this is an oscillating system, and this is also an oscillating system. Whenever you have an inductor and a capacitor, then you can expect oscillations. Okay? And you have a resistor also here. So this is an Lcr circuit or RLC circuit. RLC circuit. And this can have a natural frequency. Tell you why. And if I have another source here, the AC source, then that will be the driving source. This is the system, and this will be the driving source. Okay, so this is like the pendulum. Okay, this is like the pendulum, and this is like my hand. This is the pendulum, and this is like my hand. So this will have a natural frequency. Okay. Let's see what will change. What amplitude are we talking about here? Okay. First, let's talk about the voltage. Okay, so the voltage V is equal to Vm sine omega t. Right? If I take an RLC circuit, then this is the applied voltage, this will have maximum and sine omega t. This will be something like this. So this is your voltage maximum. Okay, or I can say a typical example could be 10 sine 2 pi f t or omega t. Okay. So this is the maximum voltage and then this is the frequency. Let's suppose I apply it here. I can change the frequency. It can be 50 Hz, can be 100 Hz, can be 200 Hz, 1000 Hz, whatever. Can change the frequency, but the maximum will not change. So, if we change the frequency, I will still have the same maximum, then it will be like this. So, this is, if we change the frequency, this is what I will get. Same maximum, 10, but then the frequency will be changing. So, I take this, I take the source, I apply the voltage across the two terminals. This is a terminal and this is also a terminal, and this is a system, so I am applying this here. What amplitude will become maximum? No, I can't talk about the voltage, because you see, whatever voltage I apply, I will get the same voltage in the system, right? If it is 0 volts, it will be 0. If it is 1 volt, it will be 1. If it is 2 volts, it will be 2. It will be 3, 3. 10, 10. Minus 10, minus 10. That would be the amplitude in the system. So there is no resonance as far as voltage is concerned. There is no amplitude variation as far as voltage is concerned, because as far as system is concerned, the system will have the same voltage as the applied voltage. But what can change? The current can change. I. So I, if you take I, then that is actually Im sine omega t plus some phi. Right? Im can change. Why Im can change? Im depends on, what is Im? Im depends on Vm and Z. Right? Im is equal to Vm by Z. Suppose if Vm is 10 as it's here, and if the impedance Z is say 5 ohms, this is 5 ohms, this is 10 volts, then Im is equal to 2 amps. So I will get something like this. I is equal to 2 into sine omega t plus, or maybe pi by 4 or 45 degrees or something, okay? I'll get that. Because I have RLC circuit, I cannot have pi by 2. So I can have some angle which is usually not 90 degrees. So I can get this. I can get something like this. Okay? So for the same voltage, for the same applied voltage, Z can change. How? Z can change in two ways. If it changes, what is Z? Z is actually R squared plus XC minus XL the whole square. So let us say I have 10 ohm resistance here, and this could be, say, at this time my XL is say 5 ohms or something, and XC in this case is going to be say 3 ohms or something. Okay. Now I can calculate my Z. Z is 10 squared plus XC3 minus 5, so minus 2 the whole square, so 4. So 100 plus 4, 104 square root would be my Z. So how can I change Z? Yeah, I can change these values, R L C. If we change those values, then Z will change. But I am not going to change R L C. They are fixed now. If suppose this is L is equal to say 10 millihenries and this is say 5 microfarads or something. That's fixed. My system is fixed. Like the length, I am fixing the resistance and then the inductance and then the capacitance values. Because if I keep them in a circuit, then I can change them, right? I have a resistance of 10 ohms connected, and I have an inductor of 10 millihenries connected, and I have 5 microfarad capacitor connected in the circuit. And now I can change. Okay. If those can be changed, can Z not be changed? No. Z can be changed even with these things. The same things I can keep changing Z. Why? Because Z is not dependent on L. It depends on XL and XC. But XL, what is XL? XL is omega L, which is equal to 2 pi FL. So for the same inductance, I can have different XLs if I can change the frequency. Okay? I can keep this as 10 millihenries, but if it is 50 Hertz, I will have one XL. If it is 100 Hertz, I will have a different XL. If it is 1000 Hertz, I will have another XL. But my L will be the same. So the system can remain the same, but XL can be changed by varying the frequency of the driving voltage. Okay? So XL will be different. And what about XC? XC is 1 by omega C, and that is equal to 1 by 2 pi FC. Okay, you can see the same thing. I can keep C the same without changing the capacitor. I can change XC by increasing or decreasing the frequency with which I drive the circuit. So these can be changed. So Z can be changed. So if Z can be changed, notice I told you that initially Z was 5 ohms. Suppose Z now is 2 ohms. For the same L and C and R, by changing the frequency, if I can somehow make that to be, instead of 5 ohms, if I make that to be 2 ohms, then my IM is going to be equal to same Vm by Z. Vm will still remain the same, 10 volts, but then only the frequency changes. Okay? Initially 10 ohms, like that. Now it is 10 ohms, like that. Okay, so you have, instead of 5, I have 2, and that will give me 5 amperes. You notice that the IM value changes. Okay? So, if I take this circuit, if I look at the voltage, here, if this is 10 volts, and if I change the frequency, I will still have 10 volts there. But if I do the graph for the current, you notice for one frequency, I will have 1 IM. Okay? For another frequency, I may have this kind of an IM. But for each another frequency, I may have like that. Okay? So you see, I can have many different IMs. This is IM1, IM2, then IM3. I apply the same voltage, but I just change the frequency. If I change the frequency, the maximum voltage doesn't change. But if I change the frequency, XL value and XC value will change for the same inductance and capacitance. And because these two things change, Z changes. Z changes. Because Z changes, IM changes. So if Im changes, I have a different curves. For different frequencies, I may have different amplitude, current flowing through it. I want you to understand this clearly. If you change the frequency, the voltage need not change. I gave the voltage the same level, 10 volts, now 50 hertz. Now same 10 volts, now I have 100 hertz. Same 10 volts, 1000 hertz. But the maximum is 10, voltage is 10, that doesn't change. But if I change the frequency for the same circuit, the same R, same L and same C, the I will be different. And for one frequency, I will reach one maximum, and for another frequency, I will reach another maximum, and for a third frequency, then it will reach yet another maximum. The maximums could be different for I. And now, you can connect this with resonance. So what did we say? There is a system and there is an external driving force, and that driving force is going to give the maximum oscillation for this system, the maximum amplitude of the oscillations for this system. So here current can do that. Voltage, no change in the amplitude. But you see, as I change the frequency with which I supply stuff, then the current changes its amplitude. And maybe for some frequency, the current will have the maximum amplitude. And that is what is called as the resonance condition. Okay, we'll talk about that now. Let me draw the Lcr circuit here. So I have resistance and then an inductor and then a capacitor here. And this is R, this is L, this is C, and I have a driving AC source. So it's B is equal to Vm sine omega t. Okay, so you'll have R ohms and then you'll have XL ohms and then XC ohms here. Okay, so your Z is given by square root of R square plus XC minus XL equals to. Okay, where XC is equal to 1 by omega C and XL equal to 1 by omega L, which is equal to 1 by 2 pi Fc, 2 pi Fl. We know this. So you can see this. If the frequency is small, let's say, the frequency goes down, then what happens? If F goes down, then XC will go up. Because F is in the denominator. So if this is a low value, then this will be a high value. And if frequency goes up, if this becomes, F becomes bigger and bigger, then XC will become smaller and smaller. So XC will go down. Okay? And look at this, then if frequency goes up, then XL will go up. And then if frequency goes down, then Xc will go down. Okay? And look at this. For some frequency, Xc will be greater and XL will be lower. So I can have some values. So this is a positive value, no? It's positive square. And for some other frequency, a higher frequency, XL can be greater and Xc can be smaller. So Xc minus XL can be a negative value, but when you square it, you will get a positive value. So notice that you can have the same Xc minus XL squared value for lower frequency and also high frequencies. Suppose there is a frequency, there is a low frequency for which your Xc is say 5 ohms and your XL is say 1 ohm. So now this is going to be Xc minus XL, 5 minus 1, 4 squared, 16, right? Can get 16 there. And for a high frequency, then your Xc, for some high frequency, your Xc can be 1 ohm. And your XL can be 5 ohm. In that case, Xc minus XL is 1 minus 5 minus 4, but when you square it, you get 2. You get 16 again, sorry. You get 16. So the second case is same as the first case. So for a low value, also you can get the same Z. R is going to be same, right? Because R is not going to be impacted by frequency. For a high value also you can get the same Z. And in between, there is a value for which your Xc can be equal to XL. There is some frequency for which your Xc can be equal to XL. So for low value, your Xc is high, your XL is low. So you will get a positive number. For a high value, you can get low Xc and high XL. So Xc minus XL will be a negative number. So you go from a positive number to a negative number equal. So you can reach 0 before you do that. Right? As you keep increasing the frequency, you will go from this positive Xc minus XL to 0 and then to negative Xc minus XL. That is what I am trying to convey here. So let us see when will you have maximum current flowing through this. So that's my I0. So I is equal to Im sin omega t plus some phi, some angle. Okay. Now, what is Im? Im is equal to Vm by Z. Vm is constant. That's not going to change. Okay. I'm going for a particular Vm, then I'm just going to change the frequencies, right? Fine. Okay. So this is equal to Vm by root of R squared plus Xc minus XL the whole square. Okay. So let's take this case. When Xc minus XL is 4, because you got, if we take this example, 5 minus 1 will be 4. 4 ohms, right? Okay. And another case where your XC minus XL is equal to minus 4 ohms, because 5 is 1 minus 5, I'll give you minus 4. Okay. So the frequency is changing from that to this, and 4 to maybe 3 to 2 to 1 difference to 0 and this. Okay. So it changes from 4 to minus 4. Okay. So now look here. Whether it is 4 or minus 4, you will get the same IM, because they are going to get squared here, right? So you will get the same IM. So for this frequency FL and this frequency FH, for these two frequencies, you will get the same IM. So when will you get the maximum IM? You will get the maximum IM when Z is minimum. When will Z be minimum? Z will be minimum when these two cancel. If this is 0, then Z will be minimum. Z will be simply R. This is 0, then Vm by R, root of R square, which is R. So that is when Z will be minimum. So the condition is Im max, I'm saying. For Im to be max, Vm by R. That means Xc should be equal to XL. So if Xc is equal to XL, this will be 0 and you will be left with Vm by R. For any other value, whether Xc is greater than XL or XL is greater than Xc, you will have some positive value added to this, because it's going to get squared. Whether it is positive or negative, this Xc minus XL is going to get squared, so you will get a positive value that will get added to the resistance. So the denominator will be a bigger number. So Vm by that will be smaller than Vm by R, because if you add anything to R square, then you are not going to get R here, it will be R plus something else. Okay. So Imax will be maximum only when Xc is equal to XL. So this is the resonant condition. So the amplitude of I alone is changing with frequency. So it will have the maximum amplitude when Xc is equal to XL. So when it has a maximum amplitude, then you say that it is in resonance. The circuit is in resonance. The system is in resonance with this source of that frequency. For the frequency at which the amplitude of the current is going to be maximum is a frequency. It's a resonant frequency, and that is a natural frequency of this too. So because resonant frequency should match the natural frequency to provide the maximum amplitude of current. Okay, so Xc is equal to XL. So what is Xc? Xc is 1 by omega c, and that is equal to omega L. So this is resonant condition. The resonant condition, then this must be true. If this is true, this will cancel. Then I have Vm by R, which is the maximum. Z will be minimum when this goes away. Vm by R, then I'll get the maximum. Okay, so I'll get I'll get the maximum current, I max, for that. So 1 by omega c is equal to omega L. So what I'm going to get here, this is going to be, I can take omega there, right? So if I take omega there, omega squared is equal to 1 by LC. So omega is equal to 1 by root LC. So this is called the natural frequency of the system. I should say this natural angular frequency. So the frequency will be in hertz, right? So this natural angular frequency is omega naught is equal to 1 by root LC. So if I have a circuit, say suppose this is 10 millihenries, and let's say this is 10 millifarads or something, okay? Then what is the natural frequency? Natural frequency of the circuit? Then the natural frequency of the circuit is, I'll say like 1 by omega is equal to 1 by root LC, root of 10 to the power minus 3 into 10 to the power minus 3. So I can get 1 by 10 into 10 to the power minus 3 to 10, right? 10 to the power minus 3. So 1 by, this is what it is. So then we go to 0.1 into then 10 cubed, so that's going to be 100. So omega is equal to 100. So 100 radians per second. That is the natural frequency of the system. I will say that if this is 10 millihenries and microfarad, this will calculate the natural frequency of the system. If I know this, then I can get F, right? So omega naught is equal to 2 pi F naught, again natural frequency in hertz, so number of cycles per second. So F naught is equal to 1 by 2 pi so this is in hertz, this is in radians per second. This is the natural frequency of the system. So I don't even have to worry about the source. If I have an RLC circuit, 1 by root LC will give me the natural angular frequency of the system. Now, if I bring an external source that is oscillating with that frequency, then I will have a resonant condition. Then the current which is flowing through this will be maximum. And that maximum current is given by this expression, this Vm by R. So L and C will drop out. They won't, because XL and XC will be equal and opposite, so they will drop out. Only this will be deciding the current. And that is also very easy to see if you can recall the phase diagram. How will the phase diagram be? Let's talk about the phase diagram. You see, this is the plane, and let's say this is I. This is the current I. So the current I is going through this, and say IM. Okay, IM. And then this is going to be VRM, right? So the voltage drop across that. But if this is IM, what will happen to this voltage, VL? That should lead the current, right? So this is like this. So I am going to get VLM here. And what about this voltage? That should lag the current. So notice here, this should be VCM. Note that VLM is always opposing VCM. So the current across the voltage across the inductor will always have a negative, the opposite sign to the voltage across the capacitor. I want you to understand that. Okay? suppose if this is, it doesn't mean they are equal. If they are equal, VLM and VCM are equal, then you are getting the resonant condition. Then it will be cancelled. Then you will be left only with VR. If current is the same, so if XL and XC are the same, then IXL, IXC will be the same, so they will cancel. Then IR will be the only voltage across this, in this circuit, across the circuit. So this voltage will be equal to this voltage in the resonant condition. In the resonant condition, these two will drop out. Okay? There won't be any net voltage across this. Okay? Voltage will be across only this resistance. And that is why all the applied voltage will be applicable only across the resistance. And because these two are getting dropped out, the current through the circuit will be maximum in the resonant condition. So the resonant condition, XL is equal to XC, which means this VL must be equal to VC in the opposite direction. If this is positive 10 volts, this will be negative 10 volts in the resonant condition. But all other conditions, if this is positive 10 volts, this will be negative 8 volts. Okay? They are not exactly cancelled. But the resonant condition, the resonant frequency, if this is positive 10, this will be negative 10. They will cancel. And all the voltage that you apply here will be here. Okay? So I want you to understand that. So this is about resonance. Let me summarize quickly. The resonant condition is the condition in which an external source is driving the system with the natural frequency so that the amplitude of the oscillations is maximum. That is resonant condition. And in this case, in the electrical circuits, the external power source is driving this system of RLC with a frequency such that the current through the circuit will have the maximum amplitude. And that happens when XL is equal to XC. The inductive reactance is equal to the capacitive reactance. In that case, XL and XC effects will cancel out and only this effect will remain. The resistance effect will remain. So when XL is equal to XC, which is a resonant condition, then 1 by omega C is equal to omega L, and omega squared into 1 by LC, so omega naught is equal to 1 by root LC, and that omega is called as the resonant frequency. So I'll call it here itself omega naught. So this is the resonant angular frequency of this system, of this circuit, the natural frequency. This is in radians per second, and I have done the same thing for cycles per second here from this. I hope this is clear to you. Okay. Now let's try to draw a graph of the maximum current versus the frequency. Let's start with this. Okay. We've just discussed that if I change the frequency in an LCR circuit, then the current will change. Why would it change? Because you change the frequency for the same inductor and for the same capacitor, the XL and XC values will change depending on the frequency. Okay, so what happens is that we have this graph. Okay, for some frequency, for one frequency, my current for one frequency I can have a current like this. So this is I. Okay. So this is my IM. Okay. This is with respect to time. So this happens for one frequency. Okay. Oh, for one omega 1, and I have it. Why does it happen? Because the XL and XC values change, are determined by the frequency omega. So I get this. And for a different omega, then I can get a different frequency, I can get something like this. Okay, now I have different frequency now. So this is my omega 2. For the omega 2, this is going to be my maximum. For the same circuit. And again I can change the omega. Okay? With this change of frequency, for the third frequency, I can get something like this. Uh-oh, I made a mistake here. For the third frequency, the current function must have come down further to the third line, pointed with the red arrow. Instead, I've stopped it with the second line along with the second frequency valley. That's a mistake. It should have come down further to the third line marked with the red arrow. Please note that. So this is for, this curve is for at different frequencies, IM. So notice that for every frequency I have a different maximum. For omega 1 I get this maximum. For omega 2 I get this maximum. For omega 3 I get this maximum. So I can draw a curve that is concerned only with the maximum, right? For omega 1 this is a maximum. For omega 2 this is a maximum. For omega 3 this is a maximum. I'm going to draw that kind of a curve, draw a graph. So it's going to be something like this. So the natural frequency, clearly for the natural frequency, I'll get the maximum IM, right? My IM is going to be maximum, or the resonant frequency, natural frequency of the circuit, and then the resonant frequency will be the frequency of the applied source, right? So I get this maximum IM, and for any other frequency it's going to be reduced. IM will be something else. Suppose this is my resonant frequency. I'll say this my omega 3 is actually omega 0. Okay. Then even if I increase the frequency beyond omega 0, then what will happen is that I'll get reduced IM only. So omega 0 is when I will have maximum. And even if I increase the frequency after that, XL may increase, but XC will come down. So that will result in reduced amplitude. That's what I'm trying to say. Okay? So this is something like that. So this will reduce. This will reduce. As I keep increasing omega, this way, this is omega 0. I will have maximum IM. And you see, this will be something like this. Same thing will happen when I decrease the frequency. As I decrease the frequency, then my omega L will be low, but my omega C, 1 by omega C will be high. My XL will be low, my XC will be high. So effectively it will still reduce the current through the circuit. So I'll have a curve like this. So this is the current curve I, but this is IM curve basically. Okay, I'm just taking one value, not all. It's not against time. Notice it is against frequency. This graph is against time. As time changes, then the current changes. But here I have taken the frequency and I have drawn the curve of IM alone. For that frequency, what's the IM? For the second frequency, what's the IM? For the third frequency, what's the IM? So that is what I have done. So this is a curve I have drawn. So the IM versus frequency curve will look something like this. So we said this. What is IM? IM is equal to Vm by R, right? R in the circuit. Or I should say, it's resonance, but I'll say Vm by Z. So what it is. So, what is the resonant current? Resonant current would be Vm by R. Resonant current, Im maximum. Im maximum is equal to Vm by R. Correct? So, if I have one value of resistance in the circuit, then I can have one Im. If I change the resistance without changing, L and C, the inductor and then capacitor will remain the same, but I am just changing the resistor alone. If we change the resistor alone, then what happens here is that my max will automatically come down. So that curve for a different resistor would be like this. So would that changing the resistor change the natural frequency? No, it won't. If we change the resistor, that has no bearing on the natural frequency or the resonant frequency of the circuit. Why? Because the natural frequency or the resonant frequency depends only on the inductor and then the capacitor. We saw that omega naught was equal to 1 by root LC. Resistor plays no role in deciding the natural frequency. So, if I change the resistor in the circuit, I can get reduced current, but that won't change the natural frequency. So I will get, if this is the maximum for one resistor, if this is the maximum for one resistor for the same L and C, and this would be the maximum for a different resistor for the same L and C. And this maximum will also occur at the resonant frequency. I want you to understand this. Think about it. It may not be clear to you immediately, but I want you to think about it. What I have done here is this. I have drawn the current graphs versus time. Different currents for different frequencies. When the frequencies change, then the currents will also change because XLs and XCs are changing. So I will have different current graphs. But for one frequency, I will have one maximum. For this frequency, I will have this maximum. For this frequency, I will have this maximum. And that is what I am plotting here. I am plotting what is my maximum value for a particular frequency. So when I do that, I get a graph like this. And the maximum I will have at the resonant frequency automatically. Understandably. And what is the second graph? And the second graph is for a different circuit that has the same L and C but a different resistor. So for that circuit also you will have the resonant frequency here, that the same resonant frequency, because L and C are the same, but resistor is changing. Because the resistor is changing, the maximum current you will get will be different. So that's the second graph. So if you keep L and C as the same, but if you keep changing the resistor in the circuit, then you will have different graphs all the time. But then all of these graphs will have the same natural frequency, same resonant frequency, and all of this graph will have the maximum value of their currents at the resonant frequency. Hope this is clear to you. Think about it. It's not easy. You have to think about it. You think about resonance and think about maximum currents and current in general, and think about the difference between this graph and this graph.